Yes. So this is a very self-indulgent talk, really. Dirk gave me a fantastic title. He said, talk about your journey into astrophotography. So it's a greenfield site, as they say. I can say whatever I like, except that I'm being recorded, so there is a limit. This is a sort of outline of the chronology, I suppose, of what I'm going to talk through. I started getting interested in astronomy when I was about 11, 12. By the time I was early teenage, I was getting a bit more serious about it. And I was an avid watcher of the sky at night at that stage, which was in black and white. So now we're dating it suitably for the younger ones in you. In fact, I checked it out. I was 17 years old before it was first shown in colour. So that just ages things a little bit for you. Black and white TV was an absolute joy, especially when you're trying to look at the colours of Jupiter and things like that. And later on, when I was, in fact, the age of my grandson sitting over there, I drove myself to an evening class in astronomy to try and sort of beef up what I knew. But that was quite fun. I mean, this is one of my, I used to, nerd, right? I was 13 and I used to keep observation logbooks of what I was seeing in the sky. This was high altitude cloud around the moon, so I was sort of plotting out what I was seeing, which boundaries were sharp and which were fuzzy and all that sort of stuff. I found that in the attic a year or so ago. It's quite fun. And then I got my first telescope. I suppose I must have been about 13 when I got this. This is pocket money territory. This is high-tech stuff, right? This was my first telescope. The key thing about this telescope is that it had a standard mounting point for a tripod, 1/4 inch. Is it SW? Can't remember. Whitworth. So I got myself a tripod as well. Now, isn't that a great tripod? It's one of the best tripods you'll ever see. But it made observing quite tricky because you have to get pretty low to the ground if you use that. So I used to do things like wedge it on top of fence posts and that sort of thing, just so I could get a bit of height. And this, this looks absolutely rubbish, and actually in many ways it is. It's full of colour distortions and all sorts of things. But with that telescope, I got my first views of mountains and the shadows of mountains on the moon. I could see the equatorial bands on Jupiter, and on a good night I could even see the 4 Galilean moons. You wouldn't get any detail, but you could see the 4 points of light to either side of Jupiter. And I could see that Saturn had rings. Couldn't see the rings, but I could see little ears on the side of the planet. So I knew they were there. And it was pretty much at that point, I think, that I was hooked. Later on, I got a Saturday job and bought myself a camera. Again, those of you of the right vintage will know what these cameras looked like. It was a 35mm Praktika. It weighed about 15 kilograms. Was hewn out of a solid piece of steel in East Germany and then shipped over to the rest of the world. But I could get star trails, I could do all sorts of stuff. And I actually tried, failed, but tried to get pictures through this with it. So I built a sort of wooden jig to hold this. I found a fitting for the tripod, and my camera was on the back of this wooden jig at the bottom. Never, ever, ever did I manage to get focus. So I gave up on that. And then what happens? You leave home, you get married, you have children, you build a career. I did absolutely no astronomy for all those years. So, that stuff sort of disappears at that point. So we're not going to talk about that. That's 50 years of my life that I'm just setting aside arbitrarily, which is a good thing, really, believe me. So here's the first proper telescope. This is after I retired. And this is, well, I've called it the Sky at Night effect. Patrick Moore used to present Sky at Night, not in the first few episodes, but later on he took over completely. And his recommendation to amateurs who wanted their first telescope was to get a 6-inch reflector. So that's what I did. That was my most recent memory of advice on getting a telescope. And I bought this from a chap who's retired and moved north now, but he had a telescope business in Sittingbourne originally. Some of you will know him. Really nice guy, full of good advice. So I got this thing set up at home, and I had enormous fun. For about a year, I just would set it out on the lawn, front or back, and just look at whatever I could see. And it was astonishing. So much stuff that you could see that you just wouldn't pick up otherwise. But then I wanted to start taking pictures. So I bought something to strap my smartphone to the eyepiece, and that's about the best I ever got of the moon through there, which was fine, but not good enough. So I'm afraid at this stage, I was beginning to fall into the rabbit hole. I had to move beyond this. So I bought myself, well, actually, no, I didn't. It was a Christmas present from my family, bless them, my first dedicated astro camera. You won't be able to see this from here, but the detector chip inside of this has a diameter of about 13 millimeters. No, it's not. It's 7 millimeters. 7 millimeters. That would be a big one. That's more that size. So there's a limitation to this, but nevertheless, this little camera, which connected over a USB 2 cable to my laptop, could take pictures for me. And I'm going to show you some of those just to show you what it could do. So here it is set up with the camera on it. And, there's an issue with reflectors. Depending on where you're pointing in the sky and whether you've done something silly like set your tripod legs too high, you end up needing steps to get up there and look at anything, which is a bit of a pain. But anyway, it worked very well. And I still use this camera now. I mean, it's so easy. I mean, it really is plug and play. It's that simple. But the next step in this journey is definitely all Dirk's fault. Shortly after I retired, we were chatting about the Beacon Observatory, and Dirk said he didn't have any volunteers to run it for periods over the summer when he was away at conferences and stuff like that. And would I let him train me to run it for those periods? And I have to say I jumped at the chance. If you want to find out a little bit more about this citizen science project that Dirk runs, have a look at those links on the screen. And it was an absolutely wonderful time. I mean, I lost huge amounts of sleep. I was little more than a trained monkey. So I wrote scripts down of what I was supposed to do, and as Dirk will tell you, I even managed to mess that up on several occasions. I didn't get calibration files right and all sorts of things. But out of that, as is the philosophy with this Hoy's Citizen Science Project, some of my data got used, and therefore my name ended up on an astronomy research paper, which is absolutely astonishing. I mean, I'm not an astronomer, but I've got my name on a paper now. So I'd recommend that. Anyone who wants to get involved in that, look it up. It is well worth doing. These 4 plates here, these are the fields that I was responsible for imaging over that summer period. And that's still part of the slideshow that makes my PC background now. I'm really proud of having been involved in that. But this was my first picture with this camera, so trying it out. It was a TV aerial about, 200 meters away. So, it's a lot easier testing new things out in daylight. And it worked quite well. I was quite pleased with that. That was great. Note the green tinge. You're going to see this a lot. The cameras you've got in your phones, in your DSLRs and so on, they're all RGB, so red, green, blue, all right? So there are filters giving you those 3 colours, which then get mixed together to produce your colour image. Astro cameras like this one have RGGB, so there's an extra green in there, which gives everything a green tint. There is a reason for that. I'm not going to go into it. you know, it all comes out in processing later on. But that's the reason you'll see green tint coming up now and again. And my first project was looking at, well, individual stars, Betelgeuse top left up there, but then some of the colourful binaries, and there's some beautiful stars out there. Almach is one of my favourites, yellow, and can you see it over here? Tiny blue dot. Very pretty. I've got Albireo up here, but actually that's not a true binary. That's they just happen to be close together in the sky, but they're pretty also. Some of them are really tough, and you might not be able to see this. This is Regulus, which is an incredibly bright star, but it is a binary. So a little bit of overexposure of Regulus, and with the eye of faith, you might see it from back there. There is a tiny blue dot, which is its binary partner down there. So that was a lot of fun. And the camera, you know, this little simple 180-pound camera was quite capable of doing that sort of stuff. And beyond that, you know, you can, I'll show you a little bit more about this later on, but this is a really easily identifiable binary system. It's part of the plough. I'll show you where later on, but it's very easy to see. But, you know, navigation was a bit hit and miss. Navigation was by star hopping, which is very good for learning your way around the sky. So you find something that's bright and prominent, or a pair of them or something, and you follow a line or a curve, or you jump up, jump down, it's part of this triangle, it's part of that quadrilateral, and you eventually find what it is you're looking for. But it's quite a jaunt. But let me just, can you see the, no, you can't see the inset on there. I'll show you where it is in a minute. The key thing to remember is that we've got this and this as the binary system that you can see. If you've got good eyes, you can see with your naked eye. It's one of the few binaries you can actually pick out that way. Pair of binoculars, it's fantastic, really easy to see. In the telescope that I was using, the reflector with that camera, you can actually see that one of those components is itself a binary. So we're up to 3 stars already. And it turns out there's so much learning to do in this hobby. It's absolutely wonderful. I love this stuff. It turns out that each of these 3 stars is itself a binary. You can't see the partner. You can see them, you know, through their spectroscopic effects, but you can't see them through a telescope. So we've got a pair circling each other here, 2 pairs circling each other there, and those 2 pairs are circling themselves, and this lot are going round in an orbit around each other as well. Incredibly complicated system, so beautiful, and to be able to see the principal components of that through, you know, what was quite a simple setup was really fascinating. So here we are. This is, right, that's the plough. Or as some people would call it, I suppose, the saucepan. There's the pan, there's the handle. And the binary that I've just showed you on the previous slide is this thing labelled Mizar and Alcor. And Mizar is the one that is itself split into 2 and fairly easy to resolve. So this is where the nerdy bit of me came out again immediately, of course. This is an inverted picture of that system. So here's the 2. This is Mizar A and B. And this is Alcor over here. So now I could, you know, test out what my field of view was. Was it like it was supposed to be? Was it like it was calculated to be? Well, actually, it's not bad. So there's almost 12 minutes in the sky between those components, and I can very easily tell now how much I can resolve in terms of fine detail. So this is a little over 14 seconds of arc between Mizar A and B. So I can start doing all sorts of little calculations like that, which for a nerdy person like me is just perfect. And I'm not sure why it's mottled like that. You'll have to ignore that if you can. There is an issue when we're trying to look at things other than individual stars, which are nice sort of points of light that move around a little bit with atmospheric turbulence, but not a lot. If you're trying to get an image of something like the moon, it's wobbling all over the place all the time, simply because of atmospheric turbulence. The higher the magnification, the worse this effect becomes. So as you can see, it's just jiggling everywhere. So how do you take a good photograph of something like that? It's really quite tricky, but one of the beauties of using a dedicated astro camera is that you can do something which usually gets referred to as lucky imaging, because you can take high frame rates. So for this simple little camera, I was very easily getting 30 or 40 frames per second of images that are, about 1080p resolution, so 2 megapixel images. Green tinge again, right? This is the moon, so same effect. But in this case, the example I dragged out, I'd taken 1,000 frames. Typically, it's more likely I'd take 2,000 these days, but 1,000 was my norm back then, which took about 6 minutes to take and load into the PC and so on. But then you can do all sorts of wonderful things with software, and I'll give you a list of the software later for those of you who are interested. But you can sort them by quality. It's a fairly crude algorithm, but it works tolerably well. So in this particular software package called AutoStacker, you get a graph, quality versus frame number, essentially. And you can select how many you want to use. So in this case, I'd selected 15%, so 150 out of 1,000 frames. And then you can stack them up. So literally, you can pile them up on top of one another and then sort of integrate them into one frame. So you're taking the 150 best frames, each of which would have taken a few milliseconds. Each frame exposure is a few milliseconds. The moon's very bright. And then stack them up and integrate them together, average them, I suppose, essentially, to get a final image. So this is where we start. So this is the integrated image. This is 150 frames all stacked up together. Still the green tint, you'll notice. But this is now going into another software package called Registax. And Registax has this wonderful little tool called wavelet refinement. So it's basically, you have to use it carefully. It's a noise reduction tool. And as every scientist knows, you can overcook noise reduction very seriously, and you can end up putting artifacts into your image rather than clearing them up. But this is the image, this is the stacked image that went in, and you'll see the difference after I've refined it a little bit. Much, much, much sharper. So it's pulled out a lot more detail now. All I've got to do next is sort out the colouring, which is fairly easy to do. I used to use Photoshop. I use something rather different now, but Photoshop used to do the job okay. And that actually looks like the moon now. So we've sort of got there. But the beauty of having an image of the moon is that I can now play with this. So for instance, if I take up colour saturation on my image, I begin to see a little bit of geology on the moon. So I hope you can see from back there, it's sort of, can you see that this lava sea is a different colour to that one? This one has a blue tinge. Sorry, it's the lighting. Do you mind if I turn the lights down a little bit? So just for this moment, all right? So you can see that's definitely got a blue tinge. That one is much more grey. It's because there are different minerals that were thrown up during the impact that made these larval basins. And you can start seeing other things as well with this, just so you can see that this impact must have come after this one, because it's actually covered it up there and made a nice new boundary. You can also tell that these craters in this one must therefore be really very recent, because they've come after that lava was formed, and that lava was formed after that lava, and so on. So that's a relatively fresh relatively fresh feature of the moon. The other thing you can see on here, I think better in this enhanced colour image, are things like this, these really bright striations coming out of some of the impact sites. And that's because material that's been hit has been liquefied, thrown up above the moon and settled back down again. And actually, just as you get on the Earth, when this sort of thing happens, it can come down as as glassy material. So actually the moon has a whole lot of glass over its surface. I mean, we're not talking about window glass and so on. It's made of all sorts of different elements and minerals. But it's one of the reasons the moon is so bright. It has this high albedo because, in part, it's got all this glass that's been distributed over its surface. It's one of the big issues faced by astronauts on the moon. This isn't ordinary dust they're picking up and taking back into their module. It's really nasty, abrasive, powdered glass, basically. So it's going to be a big problem if they're serious about building a base on the moon. Handling that dust is going to be pretty difficult. So I started pointing inwards. This is Venus. This is Venus near... it's about as much as you'll ever see of Venus, all right? Because it gets too close to the sun when it's being illuminated more than this. So this is about half of Venus, still incredibly bright. And looking outwards, Mars, that was quite fun as well. You won't be able to see it back there given what I've just noticed, but you can actually see some of the ice on the polar cap on that image, which again, from this diddy little thing and my 6-inch reflector, was quite something to be able to observe. Really good fun. Further still, we're out to Jupiter now, and its 4 Galilean moons. As I say, we're really talking about quite simple equipment here, and just using this software. All of the software I've shown you so far is free. All right, so it's not as if it cost an arm and a leg. Saturn. A lot of you will know, actually, that the tilt relative to the Earth of Saturn changes over time. So, in fact, this year, the rings are going to almost disappear. It's got to the point where it's almost edge on to the Earth. So this was back in, where was this, September 21. And you could still see the rings quite clearly. In fact, you can see the Cassini division between the two principal rings of Saturn there. But it's going to look almost ringless now. But again, with an image, you can start playing nasty tricks. So I took the processing of this image to a level that is really doing violence to the image. So here's Saturn that I've blacked out here, but I can actually pick out 5 of Saturn's moons as well, which you'd never see otherwise. You'd have to have this data to be able to do it. So we go further still, Uranus and Neptune. Again, these are absolutely tiny, right? They're a long way away, 4.5 billion kilometers in terms of Neptune's distance. So we get this beautiful bluey-green Uranus in the eyepiece. It's absolutely stunning to look at, and much more prominently blue in the case of Neptune. Beautiful. So I told you I'd mention the software. There's a lot of software, all right, to do various bits and pieces. So in terms of planning where I'm going, and again, a lot of you, I'm sure, will be familiar with these things, but I'm going to list them here just in case. Stellarium is you can get it via the web on your PC. You can get an app on your phone. Quite good for identifying things. I tend to use something called Carte du Ciel. It was recommended to me by someone from the Ashford Astro society, and I've come to love it actually. But then all sorts of other little things that you can add to this to do your calculations and predictions and so on for you. And I'll show you some of these later on as they come up. But in the last few years, as we've approached solar maximum, for instance, this one here, the space weather site, has been really good. It'll enable you to identify sunspots and other active regions on the sun. Astrometry.net is great for identifying things if you don't know where you are, as it were. And then on my phone, when I'm outdoors, I've got a whole stack of maps. But, you know, there's lots of apps that will let you point your phone and it will tell you what you're looking at. And that's, you know, that's actually really useful. Incredibly useful. I get very lazy these days. I used to try and navigate my way around the sky, but I switch on my phone now, I'll be honest. The lunar map one is fantastic for showing you where you are on the moon, as it were. And these two at the end, invaluable. One of the things you always need to know as an astronomer is what the weather's going to do through the night. The Met Office one isn't bad. Weather and radar is fantastic. Dirt put me onto this one because it gives you cloud radar images. So it'll take the previous 90 minutes and project it forward for the next 90 minutes. And it's actually pretty good at telling you whether clouds are about to be rolling in or not. And I use that one a lot. This bit of software up here is fantastic for doing things like identifying which Galilean moons you're looking at. So for any time, date, position on the Earth's surface and so on, it will give you that sort of information. It'll do the same for the moons of Saturn and lots of other stuff. This Sky and Telescope website is incredibly useful, and I'd certainly recommend it. And for actually capturing the images, I use something called SharpCap, which is one piece of software you do have to pay for. I think it costs a grand total of £20 a year now, so it's not going to break the bank. And I've mentioned already the image processing stuff that I use down at the bottom. As I say, I've pretty much stopped using Photoshop now. Photoshop is silly expensive, and I refuse to pay an annual charge to use it. So I've switched to Affinity Photo 2, which pretty much does the same stuff for a one-off £60, I think, payment. So pretty good value, really. Now, it had a restricted field of view, this camera. So here's the point at which you start taking out a second mortgage. That one was £180 and it was a joy to use, but in terms of looking at the moon, that's pretty much all I could get through the reflector and that camera. So, you know, it's essentially that image there. Now, even that's quite pleasing. I reckon I could see features on the moon down to about 5 kilometres in this system, which I was quite pleased with. That's quite a small feature. Going to be tricky. I'm going to turn these lights off again because it's worth just seeing what you can get out of something this simple. So that's the Sea of Serenity down there, and then we go up through the Caucasus. The moon has its own Caucasus range, the lunar Alps up there, and that's referred to as a alpine valley. It's actually a collapsed lava tube, but you know, it looks like a valley. So you can pick out loads of stuff, and if you get the processing right, there's a huge amount of fun to be had. But even for this image of the crescent moon with that camera and telescope, I think this is an addition of 5 different frames that I've had to stick together, and that's a bit of a pain. That's actually quite a nuisance to have to do that every time. There are lots of websites. This is one I use a lot, which will calculate things like fields of view for you. So you put in the details of your telescope and camera and it'll tell you what you're going to get out, which is quite useful. So I'm going to go back to the plough again So here it is. There's the box bit and the arm. The arrow is pointing to the MESAR-Alcor binary group I showed you earlier. This was taken just with my smartphone, all right? So you can do a lot with a smartphone. I've taken quite a few pictures on an old smartphone that I keep for this purpose. The key thing is to keep it steady, so it's got to be mounted on a tripod. And preferably sound activated shutter, so you don't have to actually touch it and make it wobble to take your image. And then it's a matter of just playing with exposures and so on. You'll find online there are guides to, you know, depending on the focal length of your lens, what's the biggest exposure time you can have before the stars start to trail in your image. I would say that's definitely an upper bound, certainly for a smartphone. So I've always gone lower than that. But it's quite useful for doing big things like that. But you can see this field of view issue now. Those yellow rectangles are the field of view that I got with this camera on my 6-inch telescope. Useless for things like this. I just about fitted in the MESAR-Alcor binary up there in the field of view, as you saw, but that was it. Seen this before? It's really quite useful as a way of measuring steps across the sky. You can look that up if you want to. It's quite useful. So I was on the hunt for a larger field of view now. And as I say, this is where it began to get a little bit more seriously expensive. This is an image, black and white image of the principal nebulae in Orion. And the black square around it is the field of view that I get with this system. Okay? And just to show you the difference, that's what I could get with my little camera there. So I could get the trapezium of young, very bright stars in the middle that's illuminating this cloud of gas and dust, but I couldn't get the cloud of gas and dust. So it has its limitations very quickly. And again, on the left, the Pleiades taken through this system, pretty much filling the whole frame. And this is what I got with the small one. Just the brightest star in the Pleiades, Alcyone, and its near neighbours. So I was desperate to get a bigger field of view. So here we are. You go from a long focal length 6-inch reflector, 1200 millimeters, to this one which has a native focal length of 555 millimeters. So we've halved the focal length. So reduce the magnification, essentially. And then I put a larger camera chip on. So I've stepped up from about 7 millimeters to a 16 millimeter diameter chip in here. So I've got less magnification, bigger camera chip at the other end. And that stepped me up. These are all images of the sun, by the way, as if you hadn't guessed already. So this is that little camera with the big telescope, tiny chunk of it. And then we step up to the new camera and shorter focal length telescope. So I can get the whole disk of the sun in now. But I can play around with this. So I can put in something called a Barlow lens, which is, I've got a 2x Barlow lens, which essentially doubles the focal length of this by adding in another optical component. So I can now get the sun to fill my frame of view, which is quite nice. This, by the way, is the active region that gave us the aurora in May. I was quite fortunate, didn't know it was coming at that stage, to have taken an image of this region, and then a day and a half later, something like that, the aurora arrived. And they come from this region that I had imaged, so that's quite nice. Bit of serendipity there. Or I can add what is called a reducer, which does what it implies. It effectively reduces the focal length. So it takes this 555 millimeters down to about 440, and I can fit a lot more in. This was a partial eclipse, by the way, that I captured in, when did I capture it? 1922. 2022. That was the joke I should have started with. So you can do lots and lots and lots. This is so flexible. I absolutely love this telescope. This was bought second-hand, by the way. Really expensive to buy new. Well, in my budget, really expensive. But actually, I bought it from the guys who run the company that make them. So it was a fairly reliable second-hand buy. So was this camera, actually. It was an ex-display model. Saved quite a bit of money doing that. These are about 850 new. So to be able to buy it second-hand saved quite a lot. So here I am on cloud-free days. This is actually set up to look at sunspots. And that's what it would look like now on its mount, with all its various cables and so on connected through to a laptop. And yes, the laptop is in a pet beach tent. It makes a great place to stick a laptop and provide shade from the sun. And actually it keeps everything dry when the humidity is going up at night time as well. It's very useful. But then we get the next barrier. There's always a barrier. I'm going to try and wind this up in 5 minutes or so. All of the stuff I've shown you so far is fairly bright and fairly easy to see. What if you want to produce an image of something you can't see? Then it gets more tricky. So there are all sorts of things available on telescopes to, the sort of so-called go-to telescopes, the little hand panel that, you can use to set it up and so on. I never had a great deal of success with that. So I have to say I now control the telescope's mount directly from my laptop, and I do it that way. But the real game changer for me was something called plate solver. So once I discovered plate solving, I was home and dry. Essentially, it takes an image of the star pattern you're looking at and tells you where you're pointing. And that's fantastic when, as I say, you're trying to find something you can't see. And SharpCap, the software I use to take these images, actually has a plate solving routine built in. So I tell Carte du Ciel where I want the telescope to point, and it gets it roughly right to within, half a degree, 1 degree, something like that, which is good enough. It can still be out of the frame. But SharpCap will then refine it through a process of plate solving. It'll look at the sky, this is where I'm pointing, but this is where I want to point, so it'll move it. Fantastic, absolutely wonderful. There are other packages that do it as well. I did try APT. So now I can get something that actually allows me to do slightly longer exposures, find things and image them. So on the left, we've got M13, which is a star cluster in the Milky Way. That contains 100, 200,000 stars. It's about 22,000 light years away. But it's quite beautiful. I messed this one up because I did it in monochrome because I took my data in the wrong file format. All my fault. I make mistakes all the time. But I still love it. These two galaxies, M81 and M82, I found almost by accident. And it's a rubbish image. And I'll tell you how to get past that. The next thing is guiding. So, more software to learn, more systems to set up and calibrate and so on. It's a good job I love this stuff. But now comes in the next camera. Actually, you could use, and I did originally use my original camera to do this, but this is now a monochrome camera. It sits on a small telescope which piggybacks on the bigger one. Can you all see that? Good. So what this does is take whatever's coming through this small telescope, it identifies stars, pinpoints them, and then it makes sure that the telescope locks onto those stars, that star pattern. So you can see behind, it's picked out several stars in its field of view, and it's now going to make sure the telescope stays with those stars kept in that position. And you can see a scatter diagram over here of one of the stars, and it's sort of drifted off a little bit, but it's keeping it fairly well confined. That first ring is half a second of arc, so it's doing pretty well. And you can see a trace of how it goes over time down at the bottom. So it's wiggling around a little bit, but actually that's not too bad. These spikes you can see on here is when something started to drift a little bit, and it just gives the motors in the mount a little kick to bring them back in line. So every time there's one of these blue or red markers, it's just kicked the telescope fractionally to keep these stars locked in position. So now you go up from a few second exposures to minutes of exposure if you need. I mean, it's a big, big step. So I can now start taking bigger and fainter things. There's a planetary nebula over there. These are stars that have puffed material out into space, so they sort of slowly expand from that. Another star cluster. This is a really interesting one. It actually moves in a strange way through the Milky Way. Apparently, this is a cluster that has been captured by the Milky Way at some time in the past. Excuse me. So it behaves peculiarly. Then there are odd open star clusters. This M39 in here is called the Pyramid cluster, and I defy you to pick a pyramid out by looking at that. I actually had to put lines in to convince myself that it was indeed a pyramid. Where these names come from, I don't know. I actually think M39 is perfectly adequate. I don't need anything else. This is, I suppose, one of my most recent ones. This is the Andromeda galaxy, our nearest neighbour, and a couple of its satellite dwarf galaxies that orbit around it. And you can see, even with this large field of view, Andromeda still, you won't be able to see it where you are, but on a screen you can see that actually I've not captured the wings fully. It's actually even bigger than the diagonal of this frame of view. And remember, the one I showed you earlier, the sun was about that size in that field of view. Andromeda is huge, but it's so faint you can't see it. So it's really rather nice to be able to get an image like this. Very pleased with it. I mentioned astronomy, astrometry.net. I'll get the words out eventually. So you can put any image, so I've put this one in, upload it to the site, and it will identify everything for you. Very useful. And actually what it showed me, which I hadn't realised until I saw this, was that the pale blue thing up there is actually a star-forming region in Andromeda. So there's some new stars being born out there in that galaxy. It's rather cool to be able to image things like that. I love it. So, next steps. What am I going to do next? Well, I can do what I do better, or I can get a robot. Some of you know how those things work. Ashley does. He's got one. It's more likely to look like that than the yellow thing that I've got. So that's my next saving project, is to get enough money together to buy one of these. Or in Ashley's case, win a competition. So that's, yeah, that's definitely the way to go. So what can I say in conclusion? It's all those words up there. It's frustrating. It's very stressful when things go wrong, and they do. It's exhausting. You can't lose many nights' sleep before you start giving up the will to live. And it is expensive. There's no getting away from it. It's expensive. And, failure is going to happen. And it happens a lot. But it's incredibly rewarding. When you get images that you wanted to capture, it's amazing. And you forget all the other stuff until something else goes wrong. It's astonishing. And, you know, I've always loved learning. This is a perfect recipe for learning. I shall never stop having to learn more about this, because it's a bottomless pit of stuff to find out. It's amazing. And, of course, it gets me in contact with lovely people like you guys. And that is the perfect point at which to say we've done. So thank you very much.